See, now we will write the total number of, see how many hyperconjugative structures we can write for this. So now we shall expand the structure first. CH3 connected to CH2, CH3. Okay. So during hyperconjugation, what happens? Wherever positive charge or double bond is there, in the adjacent carbon, okay, the adjacent carbon, how many ever hydrogens are there, they are involved in the sigma bond connecting the C and H. Okay, it actually it is parallel to, becomes parallel. This sigma bonds are capable of free rotation, right? So in turns, these hydrogens connected to the carbon, they become parallel to the empty p orbital present in this. See, because of the positive charge, there is a vacant p orbital on this carbon. So this vacant p orbital on this carbon and this the orbital forming the sigma bond here, they become parallel to each other, and the transfer of electron from here to here, that is sharing of electrons between these happens, resulting in the formation of pi bond. The sigma bond gets converted into a pi bond into this position, connecting this carbon and this carbon. So that stabilizes. So due to the shift of electron from here to here, the positive charge on the carbon gets reduced, resulting in its stability. Okay, so the number of hyperconjugative structures we can write for this depends on how many hydrogens are present on the adjacent carbon. So this hydrogen will involve in one structure, this hydrogen and this hydrogen. So 3 hyperconjugative structures are present on this side, and in this side also there is a carbon, adjacent carbon. So it contains 2 hydrogens. So these 2 are also involved in hyperconjugation. So totally we can write 5 hyperconjugative structures. Okay, for this. And these hydrogens, on this carbon will not be involved because it is away from the carbon containing positive charge. Only the carbon close to the carbocation, carbon containing positive charge, will be involved in hyperconjugation. Hydrogens present on it. Okay, so let us write the hyperconjugative structures. Just write the ring. This is cyclohexane ring. It's not a benzene ring. So C, double bond C, and since the sigma bond here is involved in resonance, we call it as no bond resonance. Hyperconjugative structures. Hyperconjugation is also called as no bond resonance. Why no bond resonance? Because in the structures, the sigma bonded electrons are involved. They get shifted to the position between the carbons. So it appears as if there is no bond between carbon and hydrogen. So this is called no bond connecting these two, right? So it is called no bond resonance. So the positive charge is held by the hydrogen now, because the bonded electrons which were satisfying the duplet configuration of hydrogen, it has totally shifted here, right? So this hydrogen lands up with the positive charge. So the positive charge here is transferred to this hydrogen, and that stabilizes the carbocation. So wherever there is, see, if a single atom is bearing positive charge, it will lead to instability of that structure. And if that positive charge is able to be delocalized through some electronic effect on other atoms, that will stabilize that positive charge species or the carbocation. So now you write the other 2 hydrogens you show by the bond. The connections are as it is. Then what you will do? These 2 you write as it is. Okay. Next, what you will do, you involve, you keep this bond as it is, and you involve now this bond in hyperconjugation. So like that. Okay. What's the next structure? You involve this one. So this will be positive. In the next structure, these two bonds will be normal. This will be hyperconjugative. I'm sorry, there is a carbon here, right? Double bond is connected to one carbon, which is having cyclohexane ring. And this carbon is in turn connected to CH. There's no hydrogen here. There is a cyclohexane ring. Then another CH2 and a CH3. We can write the CH3 as it is. No need to show the bond separately. And now you go to this side. Now we have finished all the hydrogens this side. Now let us go to the other one, other carbon, at the other side carbon. So you leave this, when you are doing the writing the hyperconjugative structures with this carbon, you leave this methyl group as it is. So first one is CH3, right? And the second one is C connected to a cyclohexane ring, and the double bond, you have to write this side. You have to put the double bond this side now. C, and one of the hydrogens as positive ion, HCH3. And the last structure would be, you write this as it is. CH3C cyclohexane ring, and again another double bond. Now this hydrogen will be involved in hyperconjugation. Another one. So totally how many structures we have written? So first structure, 1, 2. See here with this, you don't consider the original one, right? How many hyperconjugative structures? 3 here. So 1, 2, the third one. This is the original structure, right? 1, 2, 3, third one, and on the right side 2. So how we have written 5 hyperconjugative structures for this. So due to this more the hyperconjugative structures, more the stability of the carbocation will be. Supposing you have another one in which this carbon, another structure of, see if they ask you to compare the stability of 2 carbocations. In one of them having the adjacent carbon having 3 hydrogens, and the other one, if these 3 hydrogens are not there, these 2 are not there, instead of this some other group is there, like CH3 is there. So this side alone hyperconjugation will happen. So you can write only 3 hyperconjugative structures. I'll show you one more structure. For example, if I have like this CH3, C, the cyclohexane ring, and C, supposing I have a CH3 here. So on that, if this carbon is bearing a positive charge. So on the adjacent carbon, this side, when you see, there are no hydrogens directly. There should be hydrogens connected directly to the adjacent carbon, okay, which is carrying positive charge. So then only we can involve it in hyperconjugation. In this, directly connected hydrogen is not there, okay. So after this carbon, to the next carbon only hydrogens are there. So this cannot, this side, on the right hand side, there is no hyperconjugation possible. But on the left hand side, to the connected carbon, there are 3 hydrogens. So we can write 3 hyperconjugative structures for this. Okay. Supposing I give one more structure, CH3, C, cyclohexane ring, positive, C, sorry, let me write like this. Let me write this group not as a methyl group. Let me write this as a tertiary butyl group. Okay. And this side I have directly connected hydrogens. So how many hyperconjugative structures are possible for this? This side not possible because there is no direct hydrogen. Here 2 hydrogens are there. So I can write only 2 hyperconjugative structures for this. So when I ask you, when in a question they ask you to compare the stability of the carbocations based on hyperconjugation, how will you write? The one having the most number of hyperconjugative structures will be most stable. So this one, the first structure on either sides, hyperconjugation is possible. So 5 hyperconjugative structures is the maximum. So this is the most stable when compared to these. Clear? Understood?